The figure beside shows a two spring assembly with equal stiffness springs. Each stiffness, each spring has a weight of 3 newtons. You may assign half of the weight on each node as shown. Node 1 is fixed on a rigid point and node 3 is at a distance of 0.7 meters from the ground as shown. What force P is needed to be applied at node 3 so that the node just touches the ground? Assume that the distance 0.7 is shown between the gap and the node and the ground before the weight of the springs is applied. Okay, so again, like I said in the previous video, first step you do is always draw out the write out the element equilibrium equations. Okay, so let's call this the spring constant K. Okay, so for the first spring, right, it is 1, 2, okay. Okay, oh, the next step, okay, sorry, the first step of doing an FEM problem is first draw your system. Okay, label the nodes, which they already did for you, 1, 2, and 3. You can label the elements, so 1 and 2. And then after that, you label the nodal displacements and nodal forces. So this is the displacement U1, U2, U3, and also the forces F1, F2, F3. Okay. Now you must write out the element equilibrium equations. So for a spring, right? Okay, for a spring like this, so U1 and U2, and this is K. Its element equilibrium equation will be okay, U1, U2. Okay. Since its nodes are 1 and 2, I will label the columns and the rows 1 and 2, 1 and 2. Then its spring constant is K, minus K, minus K, K. Okay, so this is spring 1. Now you go to spring 2. So it's surrounded by nodes 2 and 3. And then its displacement will be U2 and U3 respectively. And it also has this identical spring constant K. Okay, so the equilibrium equation will be 2, 3, 2, 3 because of the nodes 2 and 3. Displacement will be U2, U3. And then the spring constant is exactly the same. Okay, it's still K. All right, so now we are in the position to draw up the global equilibrium equation. So since it has 3 nodes, we open a 3 by 3 matrix. So 1, 2, 3, 1, 2, 3. Then we fill up the entries. So the first matrix here says to focus on rows 1 and 2, columns 1 and 2, right? So row 1, column 1 is K, row 1, column 2 is minus K, row 2, column 1 is minus K, and row 2, column 2 is K. So let's go ahead and do that. So it is K, minus K, minus K, K. The next matrix says row 2, column 2 is K, row 2, column 3 is minus K, row 3, column 2 is minus K, and row 3, column 3 is K. So wherever there are overlapping entries, you add them. So plus K, minus K, minus K, and K. So the middle here, K plus K is just 2K. Right? Next, you fill in the displacement vector. So U2, U3, U1, U2, U3. And then next is the loading vector. Okay, so the forces, which is F1, F2, F3. Okay, so now what we can do is we substitute in the known values, right? So K is said to be having a value of 10, right? Okay, so if you do that, this will be 10, minus 10, minus 10, and 20. This will be -10, and 10. Okay. Do we know the forces? We do, right? The force, okay, for example, look at each of the nodes to find out the forces. On node 1, we have R1 plus this 1.5. Okay, so the first loading will be R1 plus 1.5. So here, R1 plus 1.5. The next loading will be on node 2, right? So it's 1.5 plus 1.5. Okay, if you find this very confusing, right? According to the diagram, node 2 has this 1.5 newtons here and 1.5 newtons here. So it's actually 1.5 plus 1.5. So let me write that down. Here it's supposed to be 1.5 plus 1.5. And you know that 1.5 plus 1.5 is actually just 3. Right? And then lastly, the force on node 3 is P plus 1.5. Okay, so if you find that confusing, according to the diagram, node 3 has a force of P and that 1.5 above it. Okay, so it's 1.5 plus P. Okay, so now we can substitute in the boundary conditions. In other words, sub in the displacements you know. They told us that node 1 is fixed in a rigid support, meaning that node 1 cannot make any displacement. Okay, so that means node 1 is a zero displacement boundary condition. In other words, U1 is equal to 0. Okay, what else? Well, we know that after the loading and after this node touches the ground, right, U3 will make a displacement of 0.7 meters, right? Because the gap is 0.7 meters, so as soon as node 3 touches the ground, U3 is equal to 0.7 meters. Okay, so let me write that down. So U3 is equal to 0.7. Okay, so now let's see if we can reduce this matrix. So if we reduce this matrix, right, what will it look like? Because row 1 is a zero displacement boundary condition, you cancel row 1 and column 1. Okay, so cancel row 1, column 1. But what about row 3? Node 3 shows a non-zero boundary displacement. Sorry, non-zero displacement boundary condition. Okay. So node 1 is a zero displacement boundary condition, whereas node 3 is a non-zero displacement boundary condition. Will that make a difference? And the answer is yes. Okay. So for a non-zero boundary displacement, non-zero displacement boundary condition, you only cancel the row. You do not cancel the column. So let me write that down. For zero displacement boundary condition, cancel both row and column. Okay, for non-zero displacement boundary condition, only cancel row. Okay, so do not cancel column. So that's the difference between a zero displacement boundary condition and a non-zero displacement boundary condition. For zero displacement, you only cancel. For zero displacement, you cancel both rows and column. For non-zero, you only cancel the row, not the column. Okay? Yeah, so that's the trick behind all of this. Okay. Yeah, so what are we left in the reduced matrix? Okay, so you see, first row is gone, third row is gone, and in the loading vector, we only have this matrix, this entry left, okay, the middle entry. We only have the second entry left in the loading vector. Okay, and how is this loading vector actually obtained? Okay, before I do any cancellation, right? Before I do any cancellation, actually, how does the left-hand side become the right-hand side? Well, you had to do the matrix multiplication. Okay, so I hope you know matrix multiplication by now. So the first entry, okay, so if you want to calculate this multiplication, right? If you want to calculate this multiplication, the first entry will become, the first entry is obtained by taking row 1 dot product with column 1. By the way, dot product, right? Okay, so dot product means I take the corresponding entries, multiply them together, and then add those products together. So what I mean, 10 times 0 plus minus 10 times U2 plus 0 times 0.7 will give me the first entry that you see here. Okay, so that's what I mean by dot product the row with the column. Okay, so that's how you obtain the first entry if you want to do the matrix multiplication on the left-hand side of this equation. Okay, so this entry is obtained by row 1 dot product with this column vector. Okay, what about the second entry? The second entry is obtained by row 2 dot product with this column vector. Okay, and then lastly, the third entry is obtained by row 3 dot product with this column vector. Okay, and that will help us obtain row 3 here. Okay, what is my point? My point is that the reduced equilibrium equation, right, is a bit counterintuitive. So what do I mean? So let me reduce this equilibrium equation again. Because the node 1 is 0, I will cancel row 1, column 1. Because the node 3 as a non-zero displacement boundary condition, I would only cancel row 3. Okay, so what we're left, right, or at least what you see that's not cancelled is this, this, and this. So you might think to yourself, well, isn't the reduced equation 20 minus 10 u2 and 3? And the answer is no. Okay, this is not the correct reduced equilibrium equation. Because if you remember, right, for two matrices to be able to multiply, for two matrices to be able to multiply, if let's say the dimension here is P, the dimension here is Q, then the dimension of the next matrix, right, must be Q by R. Okay, so you see, P by Q times Q by R. You see the entries, I mean the dimensions here match. Okay, the dimensions here must match. Okay, and in the end of the day, at the end of the day, they will produce a P by R matrix. Okay, so for matrix multiplication to be valid, yeah, these two dimensions must be equal. Okay, but let's investigate what we saw here. So here, right, see, this is a 1 by 2 matrix. This is a 1 by 2 matrix. It has 1 row, 2 columns. This is a 1 by 1 matrix. So you see, the two middle dimensions do not match. Therefore, this matrix multiplication is invalid. Okay, this matrix multiplication is invalid. So actually, the reduced equilibrium equation, right? How do we write it out? Okay, what you have to know is the entry here, the row 2 entry here is obtained by taking row 2 dot product with this column vector, right? So let us write that down. Minus 10, 20, minus 10, 0, u2, 0.7 equals to 3. Yeah. Okay. So when you check the dimensions, so this is a 1 by 3 matrix, and whereas this is a 3 by 1 matrix. So you see, they will cancel to form a 1 by 1 matrix, which is what you see here, right? This is a 1 by 1 matrix. So yeah, this is the reduced equilibrium equation. Okay, this is the reduced equilibrium equation. So when you do this matrix multiplication out, okay, so meaning to say you take minus 10 times 0 plus 20 times u2 plus minus 10 times 0.7. At the end of the day, what you get is 20 u2 minus 10 times 0.7 equal to 3. Okay, you see the only unknown in this equation is u2, so you can solve for u2, and what you get is half. Okay, and that's the answer for, I mean, at least that's the displacement for 2. But we're asked to find p, right? So that's not the end of our job yet. So let's find the value of p. So how do you find the value of p? Okay, so we already found u2, right? So we're going to substitute u2 is equals to half, which we found earlier. Okay, we substitute it into this equation here. So here we have 10 minus 10 minus 10, 20. Here's minus 10 minus 10, 10, 0, half, 0.7. Okay, so what we are gonna do is, you see, all the entries in this matrix are known. So you just do matrix multiplication. Okay, just perform matrix multiplication to multiply this to our matrix multiply. Then when you do this multiplication, what you'll get is minus 5, 3, 2, right? Equals to the right hand side. So the right hand side, just copy it down. And as you know, if two matrices are equal, then their corresponding entries are equal. We're interested to find P, right? So just take a look at the third row. So the third row says 2 is equal to P plus 1.5. Therefore, P is equal to 0.5 newtons, which is the answer. Yeah, okay, so P is equal to 0.5. Okay, that's the end of this tutorial. So if you like what you see, and if you found this tutorial to be helpful, you can donate to me on PayPal to support the growth of this channel. Yeah. So let me recap with you the steps in doing FEM problems. It's very simple. Firstly, draw out the problem. Okay. Next, you label the nodal displacements and the nodal loads. Next, for each element, you write out the global equilibrium, the element equilibrium equation. These are standard formulas which you can get from the lecture. Okay, there's no need to derive them. You simply apply them. Okay, apply them and do it correctly. When I say correctly, I mean fill in the correct labels here, and fill in the correct displacements here, and fill in the correct spring constants here. Okay, do this for the next and all the other elements that you see. And then after that, the next step is to assemble them. So assemble them means you combine them into the big matrix. So how to determine the dimension of the matrix? You look at how many nodes you have. Well, here I have 3 nodes, therefore I make a 3 by 3 matrix. 3 by 3 stiffness matrix here. Okay, assemble them by taking the entries of the element equilibrium equations, then substitute the loading conditions, which is given in the question, substitute the boundary conditions or the displacements that are known. Okay, this is usually inferred from the question or given by the question. And then after from this, you can reduce the global equilibrium equation. So wherever there are values here in the displacement vector, you cancel the rows. However, for the special case of a 0 displacement, you can also cancel the corresponding column. Okay, then you write out the reduced equation, and then you solve for whatever you need to solve. Okay, so that's how you solve an FEM problem.